Okay, this is my first video here using the technology called, I think it's called Screencast-O-Matic. It's free, and I'm going to be using PowerPoint for the background here. And I want to apologize in advance if this isn't the best video. It's my first shot at this. So this particular presentation will be over section 2.1, which is on set theory. Some of the vocabulary terms that we're going to be looking at today are set, what is a set, elements of a set, the roster method and the set builder notations for sets, the cardinal number of a set, a subset, equality of sets, the universal set, and the complement of a set. First, let's talk about what a set is. The definition for a set is a well-defined collection of objects. Here are a couple of examples. We could talk about the set of all prime numbers P, and we could also talk about another set. We'll call it C, which would be the set of all Colts football players during the 1991 football season. The prime number set would be a pretty large one. It wouldn't be something we would want to deal with in this course because it's an infinite set. Okay, now sets are made up things called elements. These are the individual objects of a set. So let's look at an example here. So let's go back to the set I mentioned in the previous slide, which is the set P of prime numbers. So let's determine which of these are actually members of that set. So let's see. I'm going to try to get my pointer going here if I can. I'm going to try. Come on. It's not going. Okay, forget the pointer. So let's look at the number 37. 37 is a prime number because it only has two factors, one in itself. So the number 37 would be an element of the set P. How about 243? 243, let's see here. That one's kind of hard to figure out if that one's a prime number. The answer is it is not a prime number, and the easy way to tell that it is not a prime number is because if you take the sum of the three digits, that would be 2, 4, and 3, you get an answer of 9, and since 9 is divisible by 3, the entire number is divisible by 3. So that's one of our divisibility tests that you may recall from elementary school. What about number 3? Is 10,315 a prime number? No, that one's a little bit easier than the last one. We know that if a number ends in 5, it's divisible by 5. So we know this one has at least 3 factors, 1, 5, and then the number itself. So the first one is an element, the second one and the third one are not elements of the set. Let's see another set example. Let T be the set of all current Perry Meridian High School math teachers. List the names of all teachers at Perry Meridian High School that are elements of T. Then let's see if we can list the name of all teachers at Perry Meridian High School that have more than 30 years of experience. Well, the first answer for number 1, we would have teachers like Mr. Allen, Mr. Brewington, Mrs. Burton, Mrs. Collins, Mr. Slack, Mrs. Jones, etc. Currently we have 17 math teachers here at Perry Meridian High School. Now, the second question says list the name of all teachers at Perry Meridian High School that have more than 30 years. So these teachers may be elements of the set T, but they may not. Notice that this one says list all teachers at Perry Meridian High School that have more than 30 years of experience. Now we do have one teacher in the math department that has more than 30 years experience. Actually, we have more than one teacher. But we also have some teachers outside of the math department that have more than 30 years of experience. How about 3? Could we do a set for this one? It says list the names of all Perry Meridian High School teachers that are difficult. See, this would not be a good definition or a good definition for a set, because how do we define difficult? Who I think is a difficult teacher, someone else may not. So that term difficult is a little bit ambiguous. If we go back to chapter 1 when we talked about statements and ambiguity, we could definitely do numbers 1 and 2. We could build those sets, but 3 we would not be able to do. Alright, so there's a couple ways to describe a set. The first method is called the roster method. And the roster method is simply listing all the elements in a set. So here is a set of baseball players. This would be what we would call a roster. And it is in a way like the roster method. It literally lists every player on this particular team. And the second method is something called the set builder notation. Now the set builder notation basically is this: specifying a name for a collection of objects and giving a rule for each of the object that each object must follow. So here, instead of listing out explicitly every element of the set, you would say, okay, here's my set S, and here is the rule for building that set. A couple of slides ago we talked about the set of prime numbers. Well, that set is infinite. Therefore, we could not really list in the roster method all of those numbers, but we could do set builder notation and say that S is equal to the set of all numbers that are natural numbers that have exactly 2 factors, and then the person then reading that would be able to build those numbers, and they would never finish because it's infinite. Here are some examples of describing a set. Here's the roster method. Now again, I did not list out all of the Parameridian High School math teachers. This is that set T I was mentioning a few minutes ago. I just listed a couple of them: Mr. Allen, Mrs. Basie, Mrs. Burton, etc., all the way through Mr. Toller. Here would be an example of set builder notation again. You could even simply say P, which would be for prime probably. And notice those are capital letters for those names of those sets. And we do use braces, and that vertical bar after the X, that means such that. So that would read P is equal to the set of X such that X is a prime number. That would be set builder notation. Which of the above sets are finite? In other words, which sets can be done with a finite number of elements? Well, that would obviously be the roster method. And then you could probably guess which one is infinite or infinite. The cardinal number of a set is simply the number of elements in a set. Okay? So for example, if we talked about the set P, now I'm talking about a different set P, and I've defined it here using the roster method. The cardinal number of that set would simply be the number of elements in that set. So if you were to count those numbers up, there's 1, 2, 3, 4, 5, 6, 7, 8. There are 9 elements in that set. So the cardinal number of that set is 9. The way we write that in notation is in, lowercase n, parentheses with the name of the set inside of it, in this case P, equals 9. And there's my cardinal. Empty or null sets. Sets with a cardinal number of 0 are called empty or null sets. Symbolically, we use a pair of braces with nothing inside of it, or we do a 0 with a slash through it. Please do not put the 0 with a slash through it inside of the curly braces. That's actually the set of empty sets. So we wouldn't want to do that. Subset. A subset, A is said to be a subset of B, denoted A subset B, if and only if each element in A is an element of B. And I'm going to see if I can get this pointer to work now, because I need to get, okay, good. This would be written in this way. It would be A, oops, I left that down too far. A, why is it not writing here? There we go. A is a subset of B, and I'm sorry about this. I don't have very good handwriting, and it doesn't help that I'm doing this on this board for the first time. That's how we would write that. And by the way, the A on the left is always the subset of the element on the right, so it always goes in that direction. So let's look at an example of that. P would be the set of X such that X is a prime number, and X is the set of natural numbers. So P would be a subset of N. And let's see if I can write that. P is a subset of N because every prime number is also a natural number. However, this would be incorrect. N is not a subset of P. This would be wrong. And the reason that would be wrong is the number 1, for example, is a natural number, and it is not a member of the prime. It isn't prime, so it's not a subset. Set equality, this is probably the most intuitive of all of the definitions, and set equality basically means that the two sets have exactly the same elements in them, or mathematically we would say that A is a subset of B, in other words everything in A is in B, and B is a subset of A, in other words everything that's in B is also in A. So all the same elements in both sets. Important rule. For any set, the empty set is always a subset. You will see that in future assessments, so make sure you make a note of that. And here I'm going to ask you to explain why. Why is the empty set always a subset of a set? Why is the empty set always a subset? Well, I tell you what, I'm going to leave you hanging a little bit on this one. I'll give you a hint, and then I'll point you in the direction if you're really dying to know. What is another way of defining a set as not a subset of another? So that's kind of the hint, and I don't know if that's just going to make you more confused. There is a website called Dr. Math. If you want to look that up and then look up empty sets being subsets, there's a nice little write-up on that, and we can talk about it in class if you'd like. The universal set, so I got a little picture of the universe down there. This is the set which contains all other sets as subsets. So, and you can, most problems or scenarios in this class, will tell you what the universal set is. So here would be an example. I could say the universal set, and by the way, we normally restrict the letter U, the uppercase U for the universal set, be the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we could say T be the set such that X is an element of the universal set and is not even. So what would those numbers be? What would be the numbers that are in U and are not even? Well, those would be the numbers. The set T then would be made up of the following numbers. Let's see if I'm trying to do a curly brace there. Be 1, 3, 5, 7, and 9. These would be the elements of T listed in roster notation. Up here above, that is actually in set builder notation. Finally, we got complement. Given a set A, its complement, denoted A prime, is the set of all elements that are not in set A. So for example, if our universal set here was 1, 2, 3, 4, 5, 6, 7, our universal set, and then we'll have another set, we'll call it P, which is 1 and 4. If I ask you to find P prime, that basically is talking about the complement, then we are looking for the things that are in, or I'm sorry, the things that are not in P but are in our universal set. So 1, which is in P, is not in our complement. 2 is in the complement. 3 is in the complement. 4 is not in the complement because 4 is in our set P. 5, it would be in our complement. 6, and then 7. So our set P prime, or P complement, would be the numbers 2, 3, 5, 6, and 7. Then below that I have another question asking about the cardinality of any set P and its complement, and does it equal the cardinality of the universal set? And that's it. I think I actually got that done. Outstanding.